Hey guys, and welcome. So today we're going to be looking at sampling the distributions of sample proportions and how all those components work. Here we go. All right, so the first problem here, we have this large candy machine has 45% orange candies. We're going to take a random sample of 25 candies from the machine and look at our sample proportion. So we know that P should be 45%. So here P is 0.45. We know that our sample is 25. So the mean of our sampling distribution, so the mean of P hat, is equal to our population proportion, or P. So if the mean of our sampling distribution P hat is equal to, so that means the mean of our sample distribution is going to be equal to the 0.45. So that is if we took many samples of all of these conditions. So that would be it for number A. For B, find the standard deviation of the sampling distribution of P hat. All right, we know we have to check on some conditions before we can do standard deviation. And the conditions is, one, are they independent samples? Meaning, does one thing impact the other? So we do have independent samples. We do need to check our 10% condition, meaning we need to check is NP greater than or equal to 10, and is N times 1 minus P greater than or equal to 10. Meaning, do we have at least 10 successes and at least 10 failures? So by having at least that many, that's our law of large counts, that will give us some normal distribution of our sample. So we need to check those two pieces. So let's see, is N times P? Well, we know here this would be N is 25 times P of 0.45, is that greater than 10? And then the same way here, in 1 minus P, so 1 minus 0.45, so 1 minus 0.45, well, we know that's, and N is 25, is that greater than or equal to 10? All right, so by doing that, we see 11.25 is greater than or equal to 10. So yes, we have at least 10 successes. Yes, we have at least 10 failures. So therefore, we know our 10% condition is met. All right, so now that we know that our 10% condition is met and we're going to satisfy our normal conditions, we can find the standard deviation of our sampling distribution P hat by using the formula, whatever the proportion is, times the 1 minus P, or sometimes they call that Q, all divided by N. So when I work that out, this would be then standard, the square root of 0.45 times 0.55 divided by 25. And that's going to give us the standard deviation of P hat is equal to 0.099. I'm just going to go ahead and put in the next digit, 5. All right, so when they're talking about the 10% condition, at first I said that was the NP is greater than or equal to 10. Well, that's not actually true. That's actually called the large counts, and that's to verify if it is fitting into our normal condition. Because we can find the standard deviation even if without it being a normal population. So we just can't find percentages or anything unless we know it's a normal. But we can find the standard deviation regardless of whether it's a normal distribution or not. So the 10% condition is simply referring, this 10% condition is just referring to, is our sample size less than 1/10 of our population size. So is the sample size less than 10%? of our population. So if we're taking a sample of 25, this is where we're going to assume, so because it is a large candy machine, we're going to assume that there is more than 250 candies. So here we would just make the assumption that there is more than 250 candies in this candy machine. So that way we know by making that assumption, because it's a large candy machine, we can make that assumption. So so you really have to write, because it's a large candy machine, we can assume that there is more than 250 candies in the machine. Therefore, our sample is less than 10% of our population. So that would be the appropriate way to answer the 10% condition. All right, here the large counts condition, we did it just a second ago to find out if it's approximately normal. So in order to check if something is approximately normal, here we're just doing NP, is that greater than or equal to 10? And is N times 1 minus P greater than or equal to 10? So do we have more than 10 successes? Do we have more than 10 failures? So that's what I started doing for part B. All right, so looking at part D, if the sample size were 100 rather than 25, how would this change the sampling distribution of p hat? Well, we knew from part C that it's normal. So if it's normal here, that means this is also going to be normal. So thinking about the shape, right? How would this change the sampling distribution? So it's only going to change. So the shape would stay approximately normal, but it is going to change our standard deviation because we're changing. So let's calculate our standard deviation here. If our sample is 100, so that would be then 0.45 times 0.55 divided by 100 instead of 25. So in other words, we made it 4 times bigger, right? So our standard deviation of p hat then becomes, so it becomes 0.0497. So what does that actually do? So we did have, our other one was the standard deviation of p hat, which we had on part B, was 0.0995. So what really happened? It just cut in half. So here, the standard deviation is cut in half. So that makes sense because we're taking the square root, right? Because we went 4 times bigger. So if I take the square root of 4 times bigger, well, if I do that, that is simply 1/2. Right? Square root of 1/4 is 1/2. So we cut it in half of our standard deviation. All right, here for part A, what is the mean of the sampling distribution? Once again, we know the mean of the sampling distribution can be, is going to be our P. So in this case, it is, so 70%. So this is going to be then equal to 0.7. And here, the reason that we say this, so the Y, is that p hat is an unbiased estimator. So this is the way to explain this. It's an unbiased estimator of our population P. So there's no bias in it, so therefore it's not going to be shifted one way or the other. So that's why we can make that assumption. For part B, when we do the 10% condition, so we're just going to check that. So the way to check that, instead of saying it out, is that, well, we have a sample size here of, so we're going to say 1,012. Well, we know that is, so I know that is less than 1/10 of all the U.S. adults, right? So therefore, our 10% condition is met. And now we can find our standard deviation of our p hat, which once again, the formula p1 minus p divided by n. So that's our 10% condition. We know that 1,012 in our sample is less than 1/10, or you could say this times 10 is less than all the U.S. adults. And I wrote U.S. students, I meant U.S. adults. So now I can calculate this. So it's going to be 0.7 times 0.3 divided by 1,012. So that's going to give me 0.0144. So that's our standard deviation. All right, to check the large counts, here we're trying to figure out if we have 10 successes or 10 failures. So NP, is that greater than or equal to 10? So is 1,012 times the 0.7 greater than or equal to 10? And is N times 1 minus P greater than or equal to 10? So do we have more than 10 successes and more than 10 failures? And obviously, in this case, we are. So therefore, we're going to have a normal distribution. All right, and make sure when you're doing this, you actually check them. So don't just write that. We want to assume that we met, yes, check, yes, we met. If I didn't put an X that we failed that condition, just to see if that holds true or not. All right, so that is our, and then we want to know the sampling distribution. Is it so the question is it approximately normal? Yes, it is approximately normal because we've satisfied our large counts condition. So yes, because of the large counts condition. All right, we have more than 10 successes, we have more than 10 failures. So we can say, yes, it's going to be approximately normal. All right, so now we come to D here, and I'm going to kind of go through a little bit of a rubric kind of guidelines for you guys to answer and make sure that you get your full points. You need a state, plan, do, and a concluding statement for these conditions. So state, we're just going to kind of restate in our own words what we're looking for in the problem. So it's kind of like, what is the problem asking us to figure out? And here we want, oops, I can't type. We want to find the probability. So we need to state something like this. We want to find the probability that in a simple random sample of 1,012 people, we're looking for 67%, so they're stating this, or fewer drink milk. And we know that based on earlier evidence that given the true proportion of U.S. adults who drink milk is actually the proportion is 0.7. So we want to find out what is that probability it'll be 67% or less. In our plan statement, we just need, here we're checking our conditions. So here we're just simply checking the two conditions. Did we fulfill the 10% condition? And we already checked that above. And did we fulfill the large counts condition? And that we already checked above. Right? So you do need to write that out, that here these were checked above, these were checked above. All right, so the do is where we're actually going to then now calculate and or draw. So you guys aren't going to have to draw on the AP, but you do need to make sure you understand what that looks like. So let's right now draw this out of what does this probability piece look like. Well, I know that when it's going to be some kind of normalized bell curve, right? So we have our normal bell curve. We know that our mean is at 0.7. And so if I go down one standard deviation or up one standard deviation, so I can say minus one standard deviation, minus two standard deviations, minus three standard deviations, where is 0.67? So we want to make sure we're clear where that is. So we know standard deviation here, p hat, was what, 0.14. So that's, so if I take that down, so I know if I take that down, so 0.60, so one standard deviation would be 0.7 minus 0.0144, right? Because that would be down one standard deviation. Two standard deviations would be that multiplied together, would be two standard deviations. And so where is 0.67 in our little bit of a spread? It's somewhere between 2 and 3. So we're looking somewhere in this range is 0.67. And now we can do our normal CDF, listing out our conditions. What is our lower bound? And here I can assume the lower bound we can go all the way down, so I know it's going to go down. So let's just say that's 0, because it's going to keep going and going and going. Our upper bound we know is 0.67, because we want to know what's fewer than that, right? Our mean of R is 0.7, and our standard deviation 0.144. So if I put all of that into our normal CDF, so I know I can do second vars, normal CDF, put in our lower bound of 0, put in our upper bound of 0.67, put in our mean of 0.77, and our standard deviation, and paste, and hit enter. And so I get 0.186. So this is saying, does the poll give convincing evidence against this claim? Right? So they're claiming that this is the case. So now we can make our conclusion that here we are going to only have, so here we know the concluding there is a 1.86% chance, so that's what this means, right? That in a simple random survey of 1,012 adults, only 67% drink milk. So that is a very, very, very small chance. So we do have significant evidence against that claim. So going anything that low in the, below in that smaller percentage, the chances of that actually happening, therefore this claim is not valid. All right, so on to the next one. Here it says sample survey interviews. 267 college women is a random sample. Here we're saying that suppose 70% of college women who've been on a diet within the past 12 months, what is the probability that 75% or more of the women in the sample have been on a diet? So here we still want to state what are we trying to find? All right, so we can make this statement. It's basically just rewording everything that we see here. Right? So we want to find the probability that in a simple random survey of 267 college women, 75% or more have been on a diet within the past 12 months, given that the true proportion of college women who've been on a diet is P equals 0.7. So that's our true proportion. So now we got to plan out, we got to fulfill our two conditions. So condition number 1, right, is did we fulfill our 10% condition? Well, we know that, so we're taking a sample of 267 college women, right? So I know that 267 of the college women is going to be less than 1/10 of all of the college women, right? Or you can say the other way around. Then we also want to double check our normal conditions. So is n times p, is that greater than or equal to 10? So NP is going to be then 267 times 0.7, and N times 1 minus P, so therefore that is greater than or equal to 10. So now we've checked our two conditions. 186.9 is greater than or equal to 10, and 80.1 is greater than or equal to 10 when we do n times 1 minus p. Make sure, once again, that when you are doing it, you do need to actually check off that you actually did that. So make sure you just use the little check marks. And then we want to find our standard deviation of our sampling distribution p hat. All right, so now we've checked our standard deviation of p hat, which we did p times 1 minus p divided by n, and then the square root. So that gives us our standard deviation. Now in the do step, now we're going to look at our normal distribution. So if I have my normal distribution here, and we're looking at 0.75, so here our mean is 0.7. We want to know where is 0.75 in that range. So if I take 0.7 and then add one standard deviation, meaning we add 0.0280, that would be one standard deviation. So at one standard deviation, I'm at 0.728, so we're past that. And then if I double this, so multiply that by 2. So at 2 standard deviations, I'm at 0.756. So I know I'm a little less than 2 standard deviations. So if I go, this would be positive 1 standard deviation, positive 2 standard deviations. I'm looking for what is it greater than this range here. So we want to know what is the probability when p hat is greater than or equal to 0.75. And so now we can do our normal CDF, do our lower bound, and here the lower bound is going to be the 0.75. The upper bound, I could make something, like, let's say 10. So that's going to be, way off. The mean going to be, way up here. So the mean here we know is 0.7, and our standard deviation is 0.0280. So standard deviation of our sampling distribution p hat. So I know if I plug that in, so here we're going to do normal CDF. We could use our lower as 0.75 because that's the lower bound of it. The upper bound, something that's really far off on the high side. Our mean is 0.7. Our standard deviation was 0.0280, and then paste. And so I get 0.037. Right. So now I can take that value and plug it in. So that tells me that my probability, p hat of being greater than or equal to is going to be 0.0373, which then I can conclude. So my concluding statement is that there is a 3.73% chance that 75% or more college women, a simple random survey of 267 have been on a diet in the last 12 months. So that would be the way to answer that question in its entirety. All right. All right. For the next problem here, we're looking at a mail order company, once again, following the state plan do conclude kind of guidelines. So we have stated now we want to find the probability that in a simple random sample of 100 orders, that 86% or less are shipped on time, given that the true proportion of orders shipped on time is 0.9. So true proportion, so company really ships 90%. We want to know what is 86% or less. Okay, so in the plan stages, we know we want to check our conditions. So we want to check our 10% condition. So 10% condition, we know that, so there's 100. So we're going to take where n equals 100. So I know that 100 times 10 is going to be less than the 5,000 orders that were shipped last week. All right, so that's checked. So we checked our 10% condition. And then we got to check the large counts condition. So in the large counts condition, that's what we're going to check to see if we have normal conditions. So is n times p less than or greater than, or equal to 10. So is n times p greater than or equal to 10, and is n times 1 minus p greater than or equal to 10. So we have 100 random samples. Our proportion is 9. Is that greater than or equal to 10? And yes, that's 90 is greater than or equal to 10. And here, this would be 100 times 0.1. Is that greater than or equal to 10? And yes, that's 10 greater than or equal to 10. So yes, we have both conditions checked there. So that's our plan stage. We did check our conditions to make sure that we can actually do the work. And we also want to go ahead and do our standard deviation of our sampling distribution p hat. So that is p times 1 minus p divided by the square root of n. So I know that's going to be then 0.9 times 0.1 divided by 100. So that's going to give me a standard deviation of 0.03. Okay, so now we actually want to actually calculate what is our standard deviation. So what is our probability? So in order to calculate probability, let's go ahead and map that out. Okay, so we know we have a normal condition because we did our large counts, which means it's approximately normal. We have a mean of 0.9, and so under a normal model, 0.9 with the standard deviation of 0.03. We want to know the probability where x is less than or equal. Oops. We want to know the probability not of x, but we want to know the probability that p hat is less than or equal to 86%. Okay, so now we can go ahead and we could do our normal CDF and label our upper bound, label our lower bound, label our standard deviation, our mean. So label our mean and our standard deviation. So let's try to figure out what is our upper bound and our lower bound going to look like. Well, I know we're looking for 86%, and I know this goes down by 0.3. So if I take 0.9, so one standard deviation, 0.9 minus our So 1 standard deviation down would give me 0.87. Well, we're below that. So we're a little bit below 1 standard deviation. So I know I'm looking for somewhere in this area. What is that area of that curve from 87 and down? So my upper bound, sorry, I got these backwards. It should be, those are backwards. Should be lower bound, then upper bound. Lower bound, then upper bound. So lower bound, I could say, is all the way down to 0. Upper bound at 0.87. Our mean is at 0.9, and our standard deviation 0.03. So that's going to give me a probability of 0.0912. Which means that I can conclude from that, this is just still all for part A, right? So we can make our concluding statement for part A now. So now I can make my concluding statement based on the 92% that there is a 9.12% chance that in a simple random sample of 100 orders, 86% or less of the orders will be on time. So that would give us our answer there for part A. All right, so for part B, it says a critic says, you claim 90%, but in your sample, the on-time percentage is lower than that, so the 90% claim is wrong. Explain in simple language why your probability calculation in A shows that the result of sample does not refute the 90% claim. So we said we got if it's 86% or less, that came out to a 9.12% chance, right? So for part A, that's what we got. So in order to refute a claim or for something to be unreasonably small, so for something to be unreasonably small, or to say that it's going to refute our claim, it has to be less than or equal to 5%. So we're above that. We are above the 5% rule. So we can't really refute it, right? So we can say this claim could be valid. We would need to take more samples to be certain. But to answer this critic, the way that would be answered, all right, so the way we would answer that then is, so since we have 9.12%, so because the probability of on-time orders is 9. And I guess we already shouldn't say that. Just say because the probability is, not even to use that, just to make sure that that's clear, is 9.12%, which isn't unreasonably small or less than 5%. It is possible that the 90% claim is correct and that the lower expected percentage is due to chance. All right, so we can go that route and answer that. So once again, it's based off the 5% rule, 5% being unreasonably small. Since we were above that, the rest of it just could be due to chance because we were going to get, right, we know that we're going to get this random bell curve. And so we could get some on the lower end of the spectrum. So, but if we got something way down at the bottom, then, less than 5%, then the likelihood of that happening is not very common. And that's why we have the 5% rule. All right, so we know for standard deviation of sample proportions, so that is the square root of p minus 1 minus p, p times 1, so square root p times 1 minus p divided by n. And so all of that's under the square root, which really we could separate that as p times 1 minus p divided by the square root of n. So the only thing that's changing here is n. We're going from 750 to 375. So in other words, we're going to 1/2, right? So I want to go to half of n. So from 750 to 375. So if I half the n, so what happens when I do 1/2 of that? So we're going to change that to then 1/2. So what is 1/2? So this would be the square root of 1/2. Well, we know when we do this, to rationalize the denominator, would just become the square root of 2 over 1. So what did we do? We increased our denominator to the square root of 2. Another way to look at that would just to take the two different variants, taking, well, 750 and 375. So if I did 750 divided by 375, well, that means that is the square root of 2 bigger. So there's our answer. It would, so decreasing the sample size, we know is going to increase the standard deviation because we're getting a bigger spread by having less samples. So we should know that instinctively, that it's not going to increase it. So I mean, it's not going to decrease the, so it's not going to decrease the standard deviation. It is going to increase because they have a reverse relationship, the sample size and the standard deviation. So as we get more samples, standard deviation goes down. As we get less samples, standard deviation goes up. They're inverse relationships. So we know, therefore, C and D can't be right because both of those would actually decrease, be less than 1. All right, last one I wanted to just go through real quick. This is a little spiral review, things that we've done a long time ago. So here we could draw our tree diagram. We have machines part A, B, and C. So it says machine A is 60%, machine B is 30%, and machine C is 10%. So it says, indicate 10% of the parts produced by machine A are defective. So we have defective or not defective. It says 10% are defective, which means 90% are not, compared with 30% defective for B, and 70% are not defective. And the same way for machine C, 40% defective, 60% not defective. So there's our tree diagram. That's part A. It says if we choose a part produced by one of these three machines, what's the probability that it is defective? So then we just got to go down. Remember how we did this? We just went down each of the little avenues or each of the little aisles. So that would be then 0.6 times 0.1. And then we got to add the next little group. That would be defective 0.3 times 0.3. And then add our last little subgroup 0.1 times 0.4. And that would be the probability that they are defective. So that would give me a 19% chance that they are defective. For part C, if the part is inspected and found to be defective, which machine is most likely to produce it? So we're saying that probability that we found that it's defective, so probability that it is, given it's defective, right? So when we say probability that we want to know what machine, given it's defective. All right, so in order to do that, we want to know what is the probability if it was A, given it's defective. And based on formula, that's the same as the probability of A and defective. divided by the probability that it is defective. So A and defective would be 0.6 times 0.1, and defective we just calculated as 19%. So A and defective would have the probability of being 3. So we got to do the same thing for B. So probability of B and defective is the probability of B and defective divided by the probability that it's defective, which is just 0.3 times 0.3, and probability defective 0.19. So that would be 0.4737. And the same thing for C. So if I took the probability that C is defective, so C, given it's defective, would be the probability of C and defective divided by the probability that it's defective, which would be 0.1 times 0.4, because that's C, divided by the 0.19, and that would give me 0.2105. So the one with the highest probability of would be machine B, because it is going to give us the highest probability of producing a defective machine, given, so likely B produced it if we picked one that was defective. All right, I know this was long and hopefully it was a little helpful, but anyway, that's it for that one. See you guys next time.